intervened the integration of measurement vector and the correlation matrix underscore real-world measurement challenges. We're using different methodologies during this research. First one is correction of inertial navigation system by external information, mutual compensation and filtering of errors of measuring instruments and measuring same navigation parameters, and optimal estimation of state vector using a priori information about the controlled process and current measurement, which implements the Kalman optimal filtering algorithm. The optimal Kalman filter became a central theme with its dual role of monitoring and filtering. The Kalman filter ensures positioning remains precise and trustworthy, delving into its application with linear systems. The Kalman filter as two-pronged algorithm stands out as a positioning standard. The covariance equations is pivotal in our study and act as a standard ensuring estimation. Leveraging redundant data from various sources, we attained unmatched positioning accuracy simultaneously of this model reflected near real-world scenarios, confirming our theoretical instincts. Our research transcends more theory and practical. We delve into tangible simulations, notably the 3D modeling of unmanned aerial vehicles missions. We go to the simulation. This is vector matrix. And this results of our simulations. These simulations ensuring real-world conditions. You can see a blue line. It's a model ideal flight position of drones, and a red line. It's modeling with bias and error of estimation of positioning of our unmanned aerial vehicles. These simulations ensuring the real-world condition from charting drone flight trajectory to assessing its reaction to elements like wind shear or weight of drone. They have an inertial model of fly. They a comprehensive picture of drone position in actual settings. Our 3D drone mission simulation resonate with nature conditions, offering a genuine gauge of UAV performance. This instincts to bring the gap between our theoretical discovering and their tangible applications. Presents a vivid case study of our findings in action. During the modeling, we have some results, main results of our small research. In summary, is findings the powers of inertial satellite positioning system amplified by Kalman filter from develop a detailed mathematical model to replicate drone emission under genuine conditions. Our research groundbreaking charter in positioning precision. We use powerful software like a MATLAB for creating a model of flight and modeling this experiment. As we progress, melding redundant data with sophisticated filters is poised to redefine positioning, establishing unparalleled standards in accuracy and dependability. Thus, the use method for redundant data sources with using Kalman filtering with characters in integrated inertial satellite positioning system makes it possible to good results of improve the accuracy, the basic navigation performance with error in range less 5 or 7%, processing the measurement in real time, using not a lot of computer memory and less computer resources. The synthesized model of drone positioning system demonstrates robust behavior and offer absolute position accuracy within 2.5 meters in dynamic flight mode after 50 seconds of system activation. Our research, we have arrived at pivotal instincts. The solutions we advocate promises a formidable positioning system, especially vital for drones maneuvering urban terrains. The Kalman filter, known for its precision in positioning data processing, emerges as transformative forces. The proposed solutions may be effective for operating of compact city drones, positioning through a busy urban environment, utilizing redundant information from multiple sources, such as GPS, ground-based beacon, or onboard inertial sensors, etc. Ensure that the drones has continuous and accurate obtaining information of its positioning, even when one source is compromised, say by tall buildings or electronic interference. Implementing correcting system in the scenarios is useful, as it not only minimizes computation overhead of the drones onboard processors, thus saving battery life and increase flight time, but also ensure timely and precise positioning and correction of navigation. Future research should explore the integration of artificial intelligence technologies with drone positioning systems to enhance precision in dynamic environment. Additionally, the fusion of multi-sensor data encompassing LiDAR and LEO satellites like OneWeb and Starlink, like a source of positioning information, may promises a comprehensive positioning solution, especially in challenging terrains and conditions. Thank you for your attention. We believe that our research has an expanded positioning system, and we are excited about the future possibilities.
Thank you very much. Thank you very much. Dear colleagues, have you a question to this article, the authors? Thank you. Thank you very much. Thank you very much, Mr.
Thank you, everyone.
Next article, next report, it is Artem Velikjanin and Inna Skarga-Bandurova, a Bresenham-based global path planning algorithm in the grid maps. So we haven't these authors: Stanislav Skorobohatko, Herman Fesenko. Edge-based sensors network for critical object monitoring.
Good day, dear colleagues. Do you see my screen well? Sorry, do you see my screen well, or?
Yes, we can see well.
Okay, so I'll start. Dear colleagues, I'm pleased to introduce our collaborative research presentation of the topic Edge-based sensor network for critical object monitoring, reliability models considering the location of failed sensor. This work is a collaboration of effort me, Stanislav Skorobohatko, German Fesenko, Vyacheslav Harchenko, and Sergei Yakovlev. Now you can see our agenda. Today we'll discuss motivation, state of the art and aim of the work and objectives and introduction section. After that, we will move forward to main results of the research and conclude our results. Motivation. Sensors network hold pivotal significance across a broad spectrum of applications, such as industrial monitoring to defense-related utilities. And despite the integral role, one key factor that influences the reliability of these sensor networks is specifically the location of some malfunction sensors. Has remained substantially unexplored. The malfunction of sensor can have noticeable implication, severely affecting the network functionality. This invariably leads to the generation of imprecise data and potential causes system breakdowns. Consequently, this is a pressing need to champion the design and implementation of robust and reliable edge-based sensors networks, which can enhance their use in multitude of critical applications. As we enter into the current landscape of relevant papers and scholarship, we find a variety of approaches that have focused on the construction of different Markov models. These methodologies are aimed to boost the particular features within such systems. Despite these commendable efforts, one finds an evident gap in the existing body of these folks. The realm of inquiry into how the placement of sensors within the network impacts system dependency appears decidedly uncharted. It is the precise gaps that our research seeks to address and elucidate future in the course of this presentation. The aim of work. Our purpose undertaking this study is to devise a proposed theoretical model that measures the ability of an edge-based sensor network deployed for critical object monitoring. We have considered different configuration to this research, embracing scenario both with and without deprecated sensors in the network. Furthermore, our model also takes into account systems inclusive of failed location aspect, as well as this where the aspect is not integral. Our intention is to provide a comprehensive model that navigates varying sensor network configuration and conditions. Our research endeavors and encapsulate within the following objectives. Firstly, we aim to design a network architecture that is empowered by edge computing capabilities and enhance the functionality of UAVs within sensor networks. Secondly, another crucial object is to create and critically examine a Markov chain-based model specific to sensor networks within these edge-enabled systems. The mathematical model will provide precise assessment of system states and transitions, contributing to the overall system's efficiency, performance, and availability predictions. Lastly, we intend to devise a comprehensive methodology that allows us to quantitatively analyze the availability and reliability of the edge-enabled system that employs our UAVs. Taking together these objectives guide of our research, propelling us towards innovate some solution for developing more reliable and efficient edge-enabled sensor networks. Now on the slide, you can see one of our diagrams. Consider the diagrams which encapsulate a Markov graph representing in sensor network composed of 9 sensors and broken down into an intricate interplay of 55 states. Interestingly, it's observed the functionality persists only in states where there are fewer than 3 indicates where there's fewer than 3 incidents of double failures within a single areas. This is a complex and nuanced scenario that demands a meticulous examination when some conducting analysis and assessment of the overall system availability. Our discussion today will take into account the complexities as we delve further in our study. Kindly note that the graph in question embodies 3 distinctive type of states. The initial states represent an instant with a single sensors in the state of failure. Moving forward, we can see the second state is an indicator of scenario with 2 sensors that have some unfortunate malfunctions. And lastly, the third kind correspondent with the situation where the 3 sensors have some succumbed to failure. The state housing 3 failed sensors invariably results in a system failure. In a related note, within the overall 36 states harboring 2 dysfunctional sensors, 12 of these contributed to a system-wide failure. This is something we need to consider as move forward in our exploration of sensor network reliability. Referring to previous slide and figure 2, we discover that graphical representation can be deslided into a more concise form for an easy understanding and interpretation. In this simplified version, we can see 5 states. The first states embody the state of system functionality at full capabilities and capacities. The second state corresponds to the situation of a single failure within a system. The state number 3 indicates the considering precision of 2 failures. State number 4 represents circumstances where 2 adjacent failures have regrettable lead to the system breakdown. And finally, state 5 symbolizes a total system failure due to some simulation recurrency. This schematic simplification aids in the efficient study and analysis of the impact of sensors failure on our system's operation. Now let's move to our case studies. Description of model. Our discussions now power towards the numerical representation of system reliability. This is governed by a mathematical matrix with the dimensionality of n equals 3. N means quantity of sensors, reflecting the vital fact that 3 simulations fail trigger a system failure. Let us envisage a sensor network consisting of 9 sensors. We tactfully represent its reliability through a 3x3 matrix structure. Within this network, the second level of our computational model houses 36 states, each corresponding to a unique combination of failing sensors. However, these combinations do not cause a total system failure. Upon the some unfortunate events, the system reach a state of failure. We find 12 distinctly identifiable states, each representing a unique scenario under which the system has malfunctioned. Within all these third-level states, the system is rendered non-functional due to the concurrent failure of 3 or more sensors. Exploring this numerical representation, we aim to better comprehend the varying levels of system functionality and failure dynamics. Having examined the various possible scenarios of sensors failures, we have thoughtfully formulated an equation. This mathematical approach will strategically calculate the probability of system availability and failure under the circumstances, providing some valuable insights into the potential flaws inherent to the network. This is a vital step toward enhancing system resilience. Upon carrying out of formulated calculation on the system configuration discussed in previous slides, we have arrived at a significant result. The computer probability of system availability is defined as 0.94 416. This matrix derived from our strategical probabilistic model unveils crucial information regarding the robustness and readiness of our existing sensor network to withstand potential failures. Result of our analysis. As we can see on this slide, we can move our attention towards the graphical representation that illustrates the correlation between the availability probability and the alternation in the failure rate of sensor expressed as the lambda. This probability change over time and clearly demonstrates the dynamic nature of our system. Upon examining the presented graph, we observe an intriguing pattern unfold. We note that incremental passage of time the system availability represents here by the probability witnesses a margin decline. This subtly yet crucial trend underscores the dynamic relationship between time and the functioning of the system, hitting in potential areas warranting future investigation and optimization. And let's shift to another significant graphical representation. This graph liquidates the relationships in between availability probability and change number of sensors denoted by N and P, representing availability. An observation surface from this visual data representation as the number of sensors in the system and in the system increases, the probability of the system's availability shows a notable decline. This downward trend underscores the critical balance between sensors quantity and system availability, suggesting potential challenges and some considerations in system design and maintenance. And let's move to our conclusions. To conclude our work, our proposed model sets some groundwork for smooth and dependable network operations, even in the face of some inventable disruptions, such as alternations in network topology or some node failures. A range of availability metrics, including some reliability or availability of our system, are examined in our analysis, enabling us to make some informed assessment about network performance. This ensures that our model is not only theoretical, but is capable of practical delivering results. The cognitive tool we have presented today has been scrutinized under two separate scenarios. Firstly, within a context where the application is permitted, and the scenario without it. And I think with our future point of progress will be exploring of models adaptability and deployment in new environments. And dear colleagues, thank you for your attention. With this, I end my presentation and waiting for your questions.
Thank you. Thank you. Dear colleagues, have you a question? Mr. Stanislav. Dear colleagues, have a question. I have some question. We have the result, your report on slide 20 and 30, maybe. How you take this result? How you take some characteristics which presented by your updating?
Okay, yeah, I understand. Mainly, it's technical characteristics of the sensors. And the first thing is, for example, some fire sensors, smoke sensors, and stuff like that. And the second one, it's results from existing works from state-of-the-art section. We take into account these results and evaluate in our work. And I think that as most of our source data for the modulation of our results.
Thank you very much. Dear colleagues, have a question? Thank you very much, Mr. Stanislav.
Yeah, thank you, dear colleagues. Really pleasure to be on this conference.
Leonid Stanislavovich, I'm glad to see you.
I'm glad to see you too.
I'm glad to see you. I'm glad to hear you. Next report, Leonid Lubchik, Galina Greenberg, and Klimenkovy. Machine learning-based predictive maintenance using data aggregation via regularized clustering. Thank you very much.
One moment. Excuse me, one moment, some problems with demonstration.
Okay.
Yes, do you see my presentation, dear colleagues?
Yes.
Yes, of course. Good day for all. Dear colleagues, I would like to present some results connected with the application of machine learning methods to the problem of predictive maintenance. It is a result obtained of the small scientific group of Department of Computer Mathematics of National Technical University KPI in Kharkov. It is a brief content of my presentations, and the main ideas I would like to discuss, it is a learning models designed for classifying and predicting failures in the predictive maintenance, and the main idea which used for develop new type of predictive models is the data aggregation via regularized clustering. And some word about the general problem. Predictive maintenance is one of the most important and well-known problems, ensuring the reliability and maintainability of a dependable system. The goal of PDM system is to implement a predictive approach to maintenance with the health state of machines constantly monitoring by network sensors. So, the problem is exactly the forecasting problem, but one have some specific features connected with the applications of the general machine learning method to the specific problem of reliability forecasting. Efficiently detected whenever the industrial equipment component has deviated from its normal operated condition or predicted them a fault, will occur as the main challenges this system aims to address. Official PDM methods promise to decrease the probability of our events, so of course it is very important from the practical point of view. Some words about the approaches. So there are two main approaches with PDM forecasting. First of all, it is model-based PDM, and another is data-driven. We will, of course, discuss only the second approach because the model-based PDM is based on the classical reliability analysis methods, and we will discuss the method of model bidding using the data, which give us the possibility to obtain it with a large sensor network. But in real world, it is very difficult to formulate an accurate theoretical model which could describe the process of degradation of production equipment. So the application of the data-driven PDM models is more important in the cyber-physical system, in the large computer system, and so on. Some words about the machine learning method which applied in this problem. This method may be divided into two main groups connected with the two main problems. First of it is so-called fair prediction problem based on current information about the state of the equipment. And another one, it is a prediction of some average or statistical characteristic of failure flows such as failure rate and remaining useful life. So the characteristic is well known. But the construction or the design, the model of such characteristic is not a very simple problem because the structure of this model at first is unknown a priori because usually we have no information in order to construct the very complicated dependence of such characteristics from some technological factors which describe the real equipment in the real world. The first problem is reduced to learning the classification of feature vectors of equipment states in the area of non-failure operation and the area of occurrence of certain type of error. So, The first problem is the typical classification problem. And the second one, of course, it is a regression problem, but tell about it is a problem very difficult because we don't know the structure of this model a priori. Statewide, there are a lot of works connected with the application of machine learning for such a problem. It is impossible to describe it in a small presentation because in fact, every method of modern machine learning now is used for such a problem. Starting from the classical Bayesian approach, logistic regression, decision tree, classical support vector machine, and so on, and ending with the modern ones such as XBoost, CatBoost, and LightGBM. But the methods directly applies to this problem not even give us good results because it is necessary to take into account the specific of the real technical problem we should consider. So the motivation of our work, the main difficulty of machine learning PDN application is to choose the structure of the learning model, the complexity of which must be consistent with the amount of available data. The significant, first, nonlinearity, and second, the complex structure of the desired dependencies determines the expenditure of using kernel-based learning methods. So we will consider special type of regressive models for the design of forecasting for the predictive maintenance. We will use the learning kernel-based model. Another problem related to the practical implementation of the design model is the need to restrict the complexity. That's the most important problem, the restrictive complexity of the model which we design, which determined by the number of kernel function used. Then using the big data sets of large volume, which is science failures are rare events. So the data set is very large in order to obtain the necessary information in order to construct the model. So the dimension of the model begins to grow catastrophically, even then using only support vector of kernel localizations. So the main idea we will propose, it is the aggregation of the data as the first step of the design of the learning system. And more exactly, the objective of our report, we develop at first a technique for classifying failures based on machine learning of aggregated data uses the technique of learning of clusters in the feature space. The proposed approach is based on the preliminary clustering of data in order to reduce the dimension of the training model. This is most simply implemented by dividing the dataset into groups corresponding to the presence and absence of failures, followed by clustering. We proposed an approach based on soft clustering approach, which allows the presence in clusters of a certain proportion of objects with a different found labels. Such approach, which can be considered as a fuzzy clusters, is very efficient for the problem we will consider. And now some words about mathematical background of our methods. First, the problem statement is classical. So we have the data set, a training data set, which consists from some vectors features. Features that in our problem is technological characteristic of the process operation. And the target labels, that is fault or fault, so it is classical classification problem, which may be used with, for example, support vector machine approach, kernel support vector machine, and so on. But the problem, it is general problem in such applications, is the find of structure of the decision functions. When we used the decision functions as a linear combination of some so-called coordinate functions of the approximation of our decision surface, it is a problem first, find the structure of this coordinate function, and the second, to find its number. All this problem is very difficult. In fact, model theory of machine learning so directed to this problem. But we will consider some heuristic approach which gives us the possibility to obtain the training model with restricted complexity. But due to the complexity of the dependence of our characteristics from the technological factors, we will use so-called kernel-based model, which directly applied to the approximation of very complex structure for our consideration. Well known that kernel-based functions and functions with have the well-known properties. It's a semantic positive definite function. For example, it may be Gaussian functions, polynomial functions. So all this result is very intensive describe and learn and study in general machine learning theory, but when we use such approach in our problem, we at first consider the classical problem. It is a problem of construction of decision surface in the feature space using the so-called support vector machine approach. So the results is a decision function which dependent from the sum set of so-called support vector. It is not all the feature vector from the training data set, it's only the subset disconnected of the localization of some of the training features which lie near the decision surface. But in situation when we'll consider from the practical point of view, our data set is not only big, it is very, very large. It is in fact big data. So the cardinality of the set of support vector may be very large too. So we proposed another approach. At first step, we propose a data aggregation of our data set in order at first to construct some clusters in feature space, and the second step of model constructions to construct the learning model not on the feature characteristic of the feature vector, but on the average characteristics, and for example the center of clusters and the average characteristic of the target function of clusters. This idea is not very new. That such approach is very often used in the machine learning problems from the big data, but we propose some specific type of the data aggregation using some type of the fuzzy clusterizations or soft clusterizations. Main idea is the following. We propose approach based on the soft clustering, which allows the presence in clusters of a certain proportion of objects with different fault labels. To do this, we use the regularized K-means clustering techniques reduced to discrete optimization problem. This is an optimization problem which gives us the possibility to construct the clusters in the feature space, and the specific functional regularization functional include not only the loss function. As a loss function, we will use the ratio loss function as a general machine learning approaches, but we use the characteristics of the distribution of any type of our objects in our clusters. And another moment, it is not obligatory to use the center of clusters as the representatives of the aggregated data set. In this capacity, weighted generalized average may be used as this proposition, and maybe use a random structure of random elements from the clusters. The randomization in these applications gives the possibility to realize the soft clusterization in the following way. And as a result, all mathematics it is impossible to demonstrate because it takes a lot of time, but only the results. It is a structure of obtain the kernel-based learning model for the predictive maintenance using at first kernel-based approach and the first preliminary clustering. It is very easy to numerical implementation of this model because all calculation at first, in fact, it is only the inversion of the some kernel matrix. It is from the point of view of correction of this problem. It is matrix with well structured. There are no problems to find the solution in such a way. Some words about the case study. We consider synthetic data set. We usually used in order to test some algorithms for predictive maintenance. Been proposed in well-known Irvine machine learning repository, and this data set consists of a large amounts of the data and characteristics the typical technological or industrial process. These 6 features, it is a temperature, process, rotational, torque, tool wear, and so on, and 6,000 with connected the different followers. So and the first step, of course, pre-processing data, we consider the statistical characteristic of data. It is very important that the data set is unbalanced, but it's only 7% failed items. So it is at first necessary to do some pre-processing of this data. Most of the features are normally distributed, unless one is the last feature. And covariance matrix, it is a hot map of the heat map of the covariance matrix, give us the possibility to perform the data cleaning of our data. Data aggregation, the main step. In such applications, the data aggregation has multiple purposes, namely reducing data set size to improve training and inference time and rebalancing data set to make resulting model more robust and simpler. At first step, is data clusterization in feature weight using target label as a regularization, and we add a restriction that the cluster could point only the same target value, or in general case, disbalance between different targets. It is the main practical idea to order to construct the soft clusterization. And the second step is to aggregate the cluster element and represent it with a smaller number of points. And numerical examples, that is example of classification model design. Our goal was to build fair prediction models based on process parameters using a classification approach. We use a well-known library sklearn. They choose SSY methods with kernel modification and use a combination of previous soft clustering with such an approach. So some words about the results. As the numerical experiments, we use 2 types of approaches. As a baseline, it is the standard classification with the use standard recall precision performance metric. And the second variant of the experiments, we use the proposed approach of previous clusterizations. This is the results of experiments. It is typical score, typical metrics which characterize the accuracy of the classification. So it is very interesting that aggregation data in fact gives the results with very similar to the using of general data. So from the point of view of the accuracy of prediction, the clusterization may be used, of course. And some illustration, it is a structure of obtained non-linear decision function. In fact, it is a separation surface in the feature space. Of course, it is a projection for some features. And this visualization describes us the possibility to obtain the very good classification characteristics of the obtained decision functions, even in the situation that the data points lie in the different section of the feature space. This is only the illustration result that they give us the possibility to obtain the understanding of the practicalization of this result. This is the distance, illustrated the distance from the separating hyperspace to the data point. The result of numerical simulation showed that despite of significant reduction of the model dimension, it was our purpose, the result of data aggregation in the training stage, it retains the ability of separate the samples corresponding to the presence of absence of failures of the group located in different regions of the feature space. And the conclusions, the paper proposed an approach to the construction of kernel methods for the classification and predictions. The aggregation is carried out on the basis of proposed clustering methods in the feature space, and the most important is the real structure of the regularizer is proposed and investigated using numerical data, and reducing the dimension of the model not only simplifies its practical interpretation, but also contributes to the acquisition of a number of additional positive properties, such as maybe smoothing of elimination of spatial oscillations and robustness with respect to measure and error. Thank you very much for your attention.
Thank you very much, Mr. Leonid. Thank you very much. Very interesting report. I hope that the very interesting and topical subject of the report interested the conference participant. Thank you very much.
Thank you.
Have a question, dear colleagues? Have a question?
Yes, I have. Can you explain me what about the number of clusters? Is this number fixed preliminary, or it depends on the dataset structure?
Of course, the problem of find the number of clusters, it is a problem of the second step of machine learning, as a find of parameters of the learning algorithm and so on. In fact, it was decided numerically using cross-validation techniques. We consider, of course, the situation when we use 2, 3, 4, and another number of clusters, and use this cross-validation, find the efficient number, which of course depended from the real structure of data set and real data. In our experiments, we obtained the possibility to use 3 clusters in our data space, but the accuracy may be improved, of course, when we consider the most complicated structure. But, of course, it may be found only using the second step of the learning, using some type of cross-validation, of course. Thank you.
Thus, I understood that it is a fitting parameter of your model.
Sorry, may I ask you to repeat, because very sound is very...
If I understood it right, that the number of cluster is a fit parameter of your model, a parameter for fitting.
You interested in the dependence of the parameters of model number of clusters?
Yes.
Yes, yes.
Yes.
Okay. We have 2 types of parameters. It is typical situation, not connected with problem. We have the parameter of the decision function, parameter of the model exactly, and we have the parameters of the algorithms. Of course, it may be a parameter of the regularization. It may be a parameter which characterizes the complexity of the decision function. It may be parameters which characterize the cluster structure of the aggregated data. And first type of parameter we find using the learning algorithm, and the second type of parameter we can find using or another data set, where data set may be divided into some groups, or using the cross-validation techniques. So at the step of the find the parameters of decision functions, it is impossible to find the hyperparameters of the algorithm as well. So it may be another problem, and they may be solved in parallel, because the final results completed all the structure, not only the decision functions, but the algorithm of the estimation.
Thank you very much.
Thank you.
Mr. Hennady, have you a question? Thank you.
Only small question. How about kernel function? What are rules for choice of kernel functions?
About the choice of kernel function. from my point of view, it is not critical because all type of kernel may be in fact give us a possibility to obtain the high quality decision function. We use a typical radial basis function or Gauss kernel function, maybe use polynomial, but all kernel functions included some parameters. It connected with the second problem is the find of parameters, not only the number of kernels, but its parameters. And what about the structure kernel? This form, it is not equal. Typical application to radial basis function, we use it, and I think it may be in practical application is very good.
Thank you.
Thank you.
Thank you for all.
Sorry, I have some question. No, maybe it is a general question. What challenge limitation did you encounter when implementing this method in real life settings?
Yes, we have some experience with real application of this method. I don't include it in this presentation because it may be another work. We have some possibility to consider the effectiveness of this method using for two applications. First of it will be analysis of the reliability of production system in semiconductor industry, because now it is a critical point of application, of course. And another, there are a lot of data, not only in public sources, but specific data connected with some real production. With our colleagues with work in this field from the Germany and in our countries, we have the possibility to consider the effectiveness of prediction of the failure rate in the semiconductors industry application. Another, it may be application, very important problem in the nuclear power plant reliability, but now it is in future. We only start with work, but in our real very hard situation now, I don't think that will continue now, but in future, of course, because we many years have the very effective collaboration with the Center of Nuclear Reliability of Ukraine, and I think that in future we continue this work. It is about the practical application.
Thank you very much. Thank you very much, Mr. Leonid. Dear colleagues, have a question. We are finishing. Thank you very much. And next report, it is Boris Pridalny. Boris Pridalny. Maybe. Sorry, we haven't these authors. We have in plan 2 articles to report Boris Pridalny, and unfortunately haven't these authors in conference. And
what's the number of the publication?
Number 74 and 63.
I will check. Maybe we can show the presentation if it's recorded. 1 second.
Okay. One moment, please, dear colleagues.
No, there is no recorded file, and I think that we can try to move this presentation to additional section, and maybe we will announce it.
Okay. And I have to ask about article number 81 and 32. Artem Vilegzhanin and Ines Karga-Bandurova. Maybe administrator have some report.
'8162, right?
Yes.
There is no such recorded file for the moment, and there is no information about the.
Okay.
Reason.
Understood it. Dear colleagues, we can finish our conference, our section. Thank you very much. I'm glad to see you. I'm glad to hear you. I'm glad to speak in this section. If administrator question, sorry.
There is no question for the moment, I think, but please check the emails in case of the sending of the extra information and about the changes in the schedule.
Okay, understood. Thank you. Thank you very much. Thank you, dear colleagues. We finished our section. Thank you very much for your work. Thank you, Mr. Gennady. Thank you, Mr. Leonid. Thank you very much. I'm glad to see you.